In this video, I'm going to share what are the factors affecting reactions rate and also Arrhenius Equation. The first factors affecting reactions rate is concentration. As the concentrations increases, basically it means that now there are more number of moles of reacting molecules per unit volume. As the number of moles of reacting molecules per unit volume increases, then frequency of collisions will increase, and this will cause the number of effective collisions to increase and the reactions rate to increase. The second factor affecting reactions rate is pressure. Pressure is applied for the gaseous reactants. As the pressure increases, means that now the reacting molecules are occupying smaller volume. As pressure increases and the reacting molecule occupying smaller volume, means that now the number of reacting molecules per unit volume increases. Hence, the frequency of collisions increases, number of effective collisions increases, and therefore the reactions rate increase. The third factor affecting reactions rate is the size of particles. So if we have a potato and the potatoes which are being chopped into smaller pieces, which one will take shorter time to cook? Definitely is the chopped one. Why? It is because as the size of the particles decreases, the surface area exposed for a reaction increases, and the frequency of collisions increases, and the number of effective collisions increases, and therefore the reactions rate will increase. The fourth factors affecting reactions rate is temperature. As temperature increases, the average kinetic energy of the reacting molecules increases, and therefore now more number of reacting molecules will have kinetic energy equal or greater than activation energy. The effect of temperature on reactions rate can be explained using Maxwell-Boltzmann distributions curve. For Maxwell-Boltzmann distributions curve, the y-axis representing the number of reacting molecules in the system, and the x-axis is the kinetic energy of the reacting molecules. At lower temperature T1, only the shaded region represent the number of molecules with kinetic energy equal or greater than the activation energy at lower temperature T1. As the temperature increases to T2, the whole curve will shift to the right to higher kinetic energy. At higher temperature, the shaded region, which represent the number of molecules with kinetic energy equal or greater than activation energy at higher temperature T2, becomes larger. So it means that at higher temperature, more number of reacting molecules with kinetic energy equal or greater than the activation energy. Again, how temperature affects the reactions rate? As the temperature increases, average kinetic energy of reacting molecule increases. That's why in the Maxwell-Boltzmann distributions curve, at higher temperature, the whole curve shifts to the right to higher kinetic energy. And as temperature increases, more number of reacting molecules with kinetic energy equal or greater than the activation energy. Therefore, at higher temperature, the frequency of collisions increases and the number of effective collisions increases and causes the reactions rate to increase. The last factor is catalyst. Catalyst provides an alternative pathway with lower activation energy. Therefore, with lower activation energy, now more reacting molecules could have the kinetic energy equal or greater than this lower activation energy. The effect of catalyst on reactions rate can also be explained using Maxwell-Boltzmann distributions curve. Without the presence of catalyst, only the green shaded region represents the number of molecules with kinetic energy equal or greater than activation energy. With the presence of catalyst, the activation energy becomes lower to EA prime, and the number of molecules with kinetic energy equal or greater than activation energy EA prime becomes larger, and this region is represented by the pink shaded region. Again, how catalysts affect the reactions rate? So catalysts provide an alternative pathway with lower activation energy. As the activation energy now becomes lower, more reacting molecules can have kinetic energy equal or greater than this lower activation energy. Therefore, the number of effective collisions increases, frequency of effective collisions increases, and this will result in increase in reaction rate. Now, we shall look at how to use energy profile diagram to illustrate the effect of catalyst in a reaction rate. Without the presence of catalyst, the activation energy is the energy difference between the reacting molecule and the transition state. With the presence of catalysts provide an alternative pathway with lower activation energy. Therefore, with the presence of catalyst, now the activation energy becomes lower. For endothermic reaction, it is the same. Without the presence of catalyst, the activation energy is the difference in energy between the reacting molecule and the transition state. With the presence of catalysts provide an alternative pathway with lower activation energy. Therefore, with the presence of catalysts, now the activation energy becomes lower. So the difference in energy between the reacting molecule and the new transition state become lower. Arrhenius, the Swedish scientist, noted that for most reactions, the reaction rate increased non-linearly with increase in temperature. He found that for most reactions, the reaction rate depends on three factors. The first factor is the fraction or number of molecules with kinetic energy equal or greater than activation energy. And the second factor is the number of collisions per second. And the third factor, the fractions of collision with appropriate orientation. He then incorporated these three factors into Arrhenius equation. And the Arrhenius equations he proposed is written as K equals to A exponential negative EA over RT, with K represent rate constant, A represent the frequency factor, E the exponential, EA the activation energy of the reaction, and R the gas constant with value 8.314 joule per mole per Kelvin, and T the absolute temperature with unit Kelvin. For the number of molecules with kinetic energy equal or greater than activation energy, in Maxwell-Boltzmann distributions curve, it is referring to the region that is shaded in green. And this region, number of molecules with kinetic energy equal or greater than activation energy, is represented by exponential negative EA over RT term in the Arrhenius equation. So what happened to rate constant K as temperature increases? In Maxwell-Boltzmann distributions curve, at lower temperature T1, the number of molecules with kinetic energy equal or greater than activation energy is represented by the green shaded region. As the temperature increases, the average kinetic energy of reacting molecules increases. This can be represented by the blue curve, which has shifted to the right to higher kinetic energy. As the temperature increases, the number of molecules with kinetic energy equal or greater than activation energy increases. This can be represented by the blue shaded region. As the number of molecules with kinetic energy equal or greater than activation energy increases, it means that the exponential negative EA over RT terms becomes larger as the temperature increases. So, the temperature increases causes the exponential negative EA over RT term becomes larger as more number of molecules with kinetic energy equal or greater than activation energy at higher temperature. This causes rate constant K to increase and reaction rate to increase as well. What happens to rate constant K when catalyst is present in a reaction? In Maxwell-Boltzmann distributions curve, without the presence of catalyst, the number of molecules with kinetic energy equal or greater than activation energy is represented by green shaded region. With the presence of catalyst, and we know that catalyst is a substance which provides an alternative pathway with lower activation energy. With the presence of catalyst, now the activation energy becomes lower, and the number of molecules with kinetic energy equal or greater than lower activation energy is represented by pink shaded region. And we can see that with the presence of catalyst, Now, more number of molecules with kinetic energy equal or greater than the lower activation energy. Therefore, we can say that the exponential negative EA over RT terms becomes larger with the presence of catalyst because the activation energy decreases with the presence of catalyst. So, with the presence of catalyst, the activation energy decreases and causes the exponential negative EA over RT term becomes larger. And this causes the rate constant K to increase and therefore the reaction rate to increase as well. Now we move on to look at how to use the Arrhenius equation to determine the activation energy of a reaction graphically. To determine activation energy of a reaction graphically means that we need to plot a linear graph. From the Arrhenius equation, how can we plot a linear graph? The only way is to modify the Arrhenius equation to get a linear equation. To get a linear equation, we can log both sides of the Arrhenius equation. After log both sides of the Arrhenius equation, we can get a linear equation written as log K equals to log A negative EA over R multiplied by 1 over T, with log K as the y-axis and 1 over T as the x-axis and log A as the y-intercept and negative EA over R as the gradient of the graph. And then from the gradient of the graph, we can then determine the activation energy of the reaction. For example, in this question, we are being given rate constants at different temperatures, and then we want to use the graph to determine the activation energy of the reaction. From the linear equations that we derive from the Arrhenius equation, we know that the linear graph we need to plot is log K versus 1 over T, with T here refer to absolute temperature with unit Kelvin. Therefore, based on the data that are being given to us, step number 1 is to convert the temperature from degrees Celsius to absolute temperature with unit Kelvin. And then we need to calculate 1 over absolute temperature. And for the rate constant, we need to calculate in the form of log K. With the data, then we can plot our linear graph log K versus 1 over T. From the log K and 1 over absolute temperature data that we calculated, we are expected to get a linear graph like this. From the linear equations derived from the Arrhenius equations, we know that the gradient of the log K versus 1 over T graph is equal to negative EA over R. Therefore, if we want to find the activation energy EA, we just need to multiply the gradient of the graph with negative gas constant value. For example, in the previous question, the gradient of the graph is determined to be negative 18,937.5 Kelvin. Therefore, to determine the activation energy, we just need to multiply the gradient of the graph with negative gas constant value to give us the activation energy 157,446 joule per mole. But for activation energy, usually the unit is in kilojoule per mole. Therefore, we just need to divide by 1000 to give us the activation energy for the reaction as 157.446 kilojoule per mole. We can also use Arrhenius equation to determine activation energy through calculation. However, this is only when we are being given two rate constants at two different temperatures that we can determine the activation energy by using calculation. If we are being given two rate constants at two different temperatures, to determine the activation energy of the reaction, we can modify the linear equations of the Arrhenius equation with K1 for temperature T1 and K2 for temperature T2. Then we minus the two linear equations of Arrhenius equation to give us log K1 over K2 equals to EA over R multiplied by 1 over temperature T2 minus 1 over temperature T1. And this equation can be used to determine the activation energy if involving two rate constants at two different temperatures. For example, in these questions, we are being given two different rate constant values at two different temperatures. Therefore, to calculate the activation energy, we can use the formula ln K1 over K2 equals to EA over R multiplied by 1 over T2 minus 1 over T1. And we can assume the first rate constant as K1 and the other rate constant as K2 and their respective temperature as T1 and T2. Must remember, T1 and T2 must be in Kelvin. Therefore, we need to convert the temperature to Kelvin by adding 273.15. And so as for temperature T2, we also need to add the temperature in degrees Celsius by 273.15 to convert the temperature to Kelvin. Then we just need to substitute all the information into the formula to get the activation energy as 114,207 joule per mole. But for activation energy, usually it is in kilojoule per mole. Therefore, we just need to divide the 1 joule per mole with 1000 to give us activation energy as 114.207 kilojoule per mole.